the last week. I certainly hope to hope that you had an impression something was fairly dramatic going on, that the activation idea can only go so far. It says nothing where the stress comes from. Okay, so what activates? Even in the spirit that you use Eyring idea, there is still a question of where the stress comes from. And once again, I have my polystyrene here. And once again, a room temperature polystyrene obviously is unable to activate and undergo so-called plastic flow, in other words, succeeding Eyring activation. So we will wrap up this part today about why styrene can be brittle, or it is brittle. And I always find it more interesting to ask the question why styrene above 70 is ductile. So this two sides of the story is the same story. Do you have a messenger? Do you have something that delivers the stress? Right? That's what we had last time. And I just, by today, find that it's just utterly transparent. The question is obviously quite let's see. The question is obviously quite turned off. Turned on. Sure that the pen is on. Okay, here it comes. All right, so let me just review a little bit, or review, meaning force you to have a sense of this. This is what you do. You grab your sample, you try to draw it at room temperature, which I mimic that by bending, and whether you can succeed in achieving that deformation really depend on whether the soldiers, whether the chains inside understand the command. And this thing just go on and on, right? Millions of them. So it looks utterly clear that the only way you can send your message through is if there is something that connects everywhere, over 1 million of such structures, right? So to the zeroth order, that seems to be also the way to think about what delivers the stress. If you really have something that's that eventually give you higher mobility, R is mobility, and match the mobility with external rate, you need something that delivers this stress, and that stress presumably is this chain network. So that's another side of asking the same question. And we are all speaking about the same thing. So if we go to the detailed picture of this, you may think about a network like this. That in addition to this chain network, of course, everywhere is frozen, is trapped. And it's this backbone that can still, it's this backbone that is sending the message. So one way of thinking about this is this backbone at least is able to display, and there is the possibility that this backbone, as it moves, there's a possibility as it moves, it will bring about movement of the surroundings. So the surrounding will start to move, the gray dots. And as you do more, all the black dots that's in dormant will start to wake up. So everything is in the same spirit. Either you speak about delivering a stress or speak about how to envision the mobility could increase, it's through this backbone. And there are millions of them now. They are all connected, not because the chain is several centimeters long, but rather because of uncrossability. They are all frozen, by the way, right, in this glassy state. So they have no way to escape. They get stuck there. So, to complete this story, right, is really to recognize that when do you lose your messenger? When do you lose the structure? And so we call this structure chain network for me to differentiate from what you learned from entanglement network. It turns out it's not the same thing. So this chain network needs to be intact. Or if not intact, need to be robust. Okay, so it can deliver. So then it's very easy to explain this point of brittle-ductile transition. Because then this point, you can, look, we can send rocket to the Mars today. We still cannot handle the problem of polymers in the sense of giving a so-called derivation of this. So this is not derivation. This is a phenomenology-inspired speculation of what really has happened. So don't tell me I have derived this. Nobody can at this point. As a result, there are plenty of people who will be unwilling to take it. But you don't need to take it if you can have a better description, a better understanding for me. And there is none. That's the point. So clearly, if you like, this brittle to ductile is one, whether this network breaks or not. On this side it breaks, on this side it does not break down. So last time I called this the Goldilocks temperature. So let's proceed and envision this moment. And if all possible, let's even be a little bit bold and envision that this is possible it is possible to even explain, just copying this, explain this stress. So this is the brittle-ductile stress, because this is the brittle-ductile point. So one could perhaps even imagine asking, what is this stress level? And then we just recall what we know from the way we think about rheology. It's a network. It's a network in the sense, this is my network. Then I claim each of this.
I use a straight line to describe that strand, but in reality, it's the red. It's more like a Gaussian chain, right? Because there's no stretching. The chain just happily stay in a Gaussian foil form. So if this is the network, all I need to ask is the area density. In other words, let me just establish the coordinate for you, x, y, z. If I look head on, in other words, if I look x, y plane, then I see these strands coming out to me, right? These, let's see, all these facing me are the red. They're coming out to me. I'm going to count them. Okay, I'm going to count them how many per unit area, and denote this by this. Since this concept is established through the idea that you have chains explicitly establish a network through uncrossability, these points, the natures of these junctions, can be regarded as arising from this, right? This point is that point. And you can argue the only way this can occur is for this chain, changing my color here, is for this chain to fold back and forth so that there could be another one coming to grab me, right? Remember that? So the argument then is that this need to be long enough for the red chain and the green chain to grab me. And how long was it? We talked about it. You need to fold several times. I know this part, I just count on you to still remember a little bit, but you can always go back to the recording to find out where they are. And we claim, roughly speaking, maybe it need to be this long. Okay? How long is that? So in our new language, we will call this load-bearing strands. Then we're really trying to figure out what is this load-bearing strand, how long it is. Well, the minimum, this is the minimum that will give you a load-bearing strand. Or let me just try to be rigorous. I would say that for this chain, this part of a chain to form, right, for this part of a chain to form, to have the possibility of becoming a load-bearing strand, you need to have a length called LC that we estimated several lectures ago. It turns out you were able to show, okay, that this length is unrelated to packing length. It's related to only the cone length. And the argument here is this is the minimum, therefore my load-bearing strand is likely to have a similar dependence on the molecular characteristics. So that's the key. That load-bearing strand, how long they will be, is going to be dictated by what your cone length is. And pay great attention to the fact that this is not P-dependent, the packing length dependent. Remember the entanglement length, which is coming from the packing model. You have to know in that packing model, there's no such a concept as uncrossability, making a hook, a double hook, a pair of hairpins.
There's no such a concept. Although, from that packing model, we can see how clouded they are. There's a critical degree of cloudedness that has to do with how long chain has become, and that's this entanglement length. This is a new universal term, entanglement spacing, entanglement length. So my book continued to use that concept, the same word that's in rheology. And that, according to the packing model, watch. The packing model conjecture precisely reduces to saying that this is proportional to the packing length. That's the packing conjecture. The consequence of packing conjecture is this. Therefore, this is the conjecture. Why do I say all this? It's very powerful. Why do I say all this? Because we're trying to figure out the area density. And we can flip back to the notes some time ago. You will find out a way to argue about area density of a network that has a strand of R is generically given simply by 1 over packing length times R. This, again, is something you can, in principle, go back to the notes early on. It's surely described in the book as well. But look how powerful. So let me introduce give me any network. I introduce a mesh size, that's R. Now, it's only a question of what this R is. See that point? Are you going to use this one? Or are you going to, or are you going to use this one? Yeah? So both claim to give you some length scale or mesh size related to the vague word of entanglement, which we sometimes also call that vague word means uncrossability. But they are not the same. They are not the same. Which one to choose? So here, recognizing the mechanical aspect of mechanical importance of this network, perhaps I want to choose this as my network unit, as the unit, building block of my network. I know this is all quite simple on mathematics, quite deep on the concept about choosing. You choose this only because the second one does not give me a vivid picture of how this network will form. Because that's just a packing model. Things just getting clouded. My mind is so murky. I mean, there's nothing I can say about what that is. Well, that's just teasing by saying that. But clearly, there is the option of recognizing the pair of hairpins, and that seems attractive and seems reasonable. Okay? And as I said, in commemoration, and that percolation model was first proposed by Richard Wu, describing some detail in the book, the percolation model. And that model, from that model, yields a building block that would suggest the low bearing strength is this, not that, which means P. In other words, my low bearing strength is proportional to cone length, not proportional to P, the packing length. Remember, I once claimed there are only two lengths important in polymer science. One is packing length, one is cone length. Now we have a choice. So, having said so much, we're getting to the deep bottom line of
avoiding any ambiguity and being very precise about the picture. In other words, prior to us, this is all worked out in 2014 GCP paper. Prior to this point, you can speak about entanglement forever. Oh, sure, entanglement is important for me to have the ability to have a fork. I know it's brittle, but it still was, we will touch it today perhaps, but still it was good enough to be used as a fork. Over time it may break. That's all because of entanglement, people will say. You will read from textbooks. But what do we mean by that? And in fact, we have the contrast of the two reasons. Okay. So the rest is quite remarkable. So let's turn one more page and continue on the question of what may determine this point. And so let's count on our luck. Let's speculate. Yeah, I want to invite you to think about this. This is how many strands are sticking out. Okay, it's sticking out as phi, as 1 over p low-bearing strand. And therefore, it is 1 over p cone length. That's what we indicated. So the force that can fight with, or that arises from the drawing is, of course, coming from the low-bearing strands. And they are, remember, stress is always force per unit area. So we are talking about force coming from each chain, each load-bearing strand per unit area. And what's left is how much force from each strand at the brittle-ductile point. What is that point? What is that point? Oh, Lord. That's the point network breaks apart, right? So, this is the force that's building up so much the network falls apart through what? Through the chains start to slide at the junction. So let's call that chain pull-out force. So the CP stands for chain pull-out. And since all this is happening deeply below glass transition, and we are now speaking about the possibility of answering this brittle-ductile transition question for all polymers. Polystyrene, PMMA, polycarbonate, PET, everything. Then the hope is that this point occurs sufficiently below TG so that there is some universality. There is something all different polymers share. What they share? Well, how about they all pull out at the same magnitude of force? That's just dreaming, okay? You hope so. In fact, you have no idea, and I have no idea. Nobody can predict. But so the logic goes both ways. You propose such a thing and see if it works. When I say it works, it turns out there are just about a dozen polymer that Vincent, who is really Vincent. He's really done some fantastic experimental work. He, in the 60s and 70s, collected a set of data for sigma ED for these dozen polymers. Okay? Not only that, he plotted this data with what is inspiring him to think about what is the structure of your polymer. And the way he did, so this is the XY plane. The way he did is he visualized all the bonds are passing. Oh, I meant to change the color. It's just so slow, the computer. All the bonds are going through. Oh gosh, this is not the right color. So they're all coming through. So if I look at my XY plane, I have all the segments coming through. All the segments. No network picture in mind, okay? Just all the segments. They're going to stick out when I make a plane cutting through. And you know exactly, and we know why he is motivated to do this. You know exactly what is the area density in this case. Remember, if you recall, each of your chain has a little cross-section we call S. Okay? There's a little section we call S. Then this density means in each cross-section of S, there will be one chain going through, right? Such that 5 times that area is 1, which is the same as saying. Okay? This is the magic that remained unresolved until a few years ago. So I'm motivated, as Vincent was plot against phi. And this is a famous plot. We should just honor Vincent called a Winston Plot. Let's go there. This is the Winston plot on the left, upper left. Of course, there's something you don't recognize because I have plotted, I have plotted against our parameter, which we just introduced, right? And Vincent, let me show you the plot. Here's the Vincent plot. Vincent plotted the number of backbone bonds per unit area, which is what I just said, phi. And look, this is the originality now. Look at what you find. It's nearly a straight line. How remarkable can this be? This is classic. However, there's a big however to it. However, this plot presumably generated
tremendous amount of confusion. It hinted at the possibility that this breaking point, brittle-ductile transition point, is all transition. Because each of the bond is going through my area. The only reason I'm motivated to plot this way is to think, actually, that all the chains breaking at the point when this breaks. This polystyrene breaks. And then we'll explain the whole 9 yards of why this is a confusion. But that was the motivation. And this implies that. Well, except we're in trouble, and which we'll explain in great detail. Except we're in trouble. Why? If this notion is correct, then this should be just the breaking force. Yeah? Right? Because I claim all the chains are going through the cross-sectional area. Each chain is requiring FB to break. And I have this many chains per unit area. So what do you find? You find the slope. The slope, of course, is F. Except this F is not FB. FB is 3 nanonewtons on the order of. In other words, to break a covalent bond takes 3 nanonewtons. Okay? Each of such bond that you can envision in your chain. All right? You know what? This, trying to translate. Let's say, where is my polyethylene? Polyethylene is here. About 106. This polyethylene, it reads this value is about 160 or 150 megapascals. Okay? It's here. It's reading. I know it's a little small. It says 160. Or if you don't like it, you can get to my reproduced plot. Polyethylene is this point. It is about 150, 160 megapascals. Okay. That's what you find in your experiment. All right? If you plug in this number and the number for polyethylene of this area density, okay, you would have find this number for polyethylene would be, instead of 160 megapascals, would be 16 gigapascals. Two order magnitude higher. Conversely, the F he find is breaking force divided by 100. That's his slope. Let me just try to recapture this. There are so many things going on, so let's take all the time there is today to do it. Basically, Winston found the plot and find the sigma BD, and he plotted as function of
of all the strands that's coming out per unit area, the phi. And he found out that this slope is only 1/100th of the force involved in this expression. Is only 1/100th of the force required to break. Okay? So one way of saying this is, oh, it didn't break because only 1% break would give you this much already, force already. Yeah? I should pause and see if you have questions on this. In which case, I just repeat. Yeah. The problem is I know it's recorded, and if you have time to listen to the recording, you will answer your own question. But why not we try to get answered now? Yeah. Yeah. Let's basically examine this Winston plot. What he plotted is stress versus the density. That's what he did. And from which you will get a slope. By definition. It has the unit of force. By definition. And you will find the Winston plot says F is about 0.03 nanonewtons, which is 100 times smaller than what it takes to break. So you can do anything you wish. You can infer, oh, it means it didn't break. Right? Because force of 0.03 is too small to break chance. Okay? Right? Reasonable? I'll come back to this, actually. I'll amplify this 1,000,000 times, if necessary, to show how poor the understanding was. But let me first come to a more interesting point to this, which is when we analyze this according to our network picture, I see we just need to go a few earlier. Get rid of this. God, I don't go anywhere. Okay, so when we envision this, we count our log, we say, gee, maybe that point is the point of network breaking, not bond breaking, not something that has nothing to do with a sense of a network, because in their sense, the network is as dense as each of the monomers that's coming out of it, right? That's obvious. So the question is whether you have the luck of showing this formula also in the limit that this is constant. Then, of course, your stress at that point of breaking, the so-called brittle-ductile transition, will be proportional to this density, right? By definition, if this is a constant at the point of breaking for different polymers. And as I indicated, this, according to the previous formula here, by plugging in R, by plugging in R, oh God, what happened? by plugging R as proportional to cone length, then this is nothing but proportional to P, right? 1 over P. Because cone length is an independent length. So what I want to say here is that we can expect, my stress to be 1 over P. Because when you look at a dozen polymer, what differentiates one from another is P. It's only P. Well, when I say that, I'm making a small insight I give you. The cone lengths are not that different between the polymers. They are all flexible polymers, linear flexible polymers. So let's go back to the plot here again, the Winston plot. You know what? Winston found this linear dependence, implying the stress is linear in phi, and therefore is linear in 1 over S. And if you recall, S is nothing but P times cone length. Therefore, amazingly, therefore, this network density, area density, has the same dependence on P as this phi does. And that's why in either plot, you will have a linear plot. The rest is also remarkable. If you plot this stress as function of entanglement network density, which says it should be 1 over P, the R is entanglement length, then it's 1 over P squared. Because the entanglement length is proportional to P as well. Okay? So if you somehow claim, oh, I know all this is just entanglement network. Entanglement network has the area density of this. And you make a plot like that. And look how ugly that plot is. It does not correlate properly or linearly. Conversely, it gives me a chance to say, my God, is this good luck or whatnot, or something more universal, fundamental, that this does appear to be a constant for all polymers. The critical force where the chain pulls out, the network falls apart. For different polymers, which of course occurs at different temperatures, is the same. Well, that's your luck. I mean, I never even had my finger crossed when I did this. But since it follows this line, it implies that F is constant. F per R. So the logic goes in reverse, okay? At least one implication is that this is the case. Oh, God, the rest, it's really too good to be true, honestly. Because you see the treatment here is a treatment of rheology per se. In other words, I don't worry about whether my all network is frozen or not.
I visualize my backbone is doing the job. I'm going to ignore anything else that's doing anything. It's just my backbone that's carrying the load. Is the result of the stress you see as a reflection of the backbone's resistance to drawing, to the deformation. Here, the gray dots that are fixing all the backbone, their function mechanically is ignored. And not just like rheology, when we had the rub elasticity. We ignore anything else floating around. We just see that backbone, which is my rub elasticity. Where in our case, without cross-linking, it's the uncrossability junction. Is this clear? This is a very simple and therefore supposedly really too good to be true. And when we say too good to be true, it's because we are not deriving it. We're speculating. We're using reasoning. We're using pictures. We learn from rheology. We learned that we need to answer the question of what delivers the stress. We need to answer the question of how mobility can improve over 10 million layers between them, because I'm not asking any monomers to gain mobility while I was just holding my sample like this and start to draw. The 10 millions in between them is not up to me to do anything about. Thankfully, if there is this network, it will sense it. Right? That's the whole point. Not only will sense it, as I cool down, I will reach a point that if the network falls apart, I will not be able to sense it. So the rest really is a discussion of over 10 million layers just below the temperature that's too cold. Then this condition of failure will be reached across this 10 million layers. Maybe the 100 layer will reach that condition first. And that's enough, because that's the place that will break. That's why you see this thing breaking so sharply. In other words, once I have this breaking, what happened to the rest? Totally intact. By definition, nothing happened. They remain as strong. So that's the horse race we learned from rheology already. But there's 10 million that are going through the same thing. Let's have a race. Let's see who wins. But that concept, of course, is highly difficult. This horse race concept to appreciate. But if you appreciate that concept a little more, perhaps you can forget about fracture mechanics, because that supposedly is teaching you how to think about failure and breaking. I'm half joking here now. Okay, any questions? So this is a nicely prepared slide of my talk, so you can see that what I was implying about drawing these gray circles. They are just cylinders wrapping around each backbone, each load-bearing strength. I'm just indicating when the temperature is above the BDT, brittle-ductile transition point, I can always cause this mobility to grow until there is enough mobility everywhere as the gray circles start to overlap. And indicating below that, you're just in that frozen state before network falls apart. So that's this, if you like, right? This state is the remaining of my polymer.
In other words, it's unable to reach a global activation, represented by the darkest shades here. Okay, any questions?
Hi, Doctor. I have a question.
Yes.
About Winston model, and it assumed that the transition is the mechanism of fracture, but why only transition he assumed? Like Chem pull-out can also cause fracture. Maybe transition is the most energy cost way for fracture.
Okay, so his question comes back to the deepest point of all. That is whether when you have brittle failure, whether it is due to transition. So, of course, if you look at this argument, it says it's not transition because transition would give you. But that argument is wrong. Is what I will criticize in the next few minutes. If you ask the bottom line about what happens, then it's quite simple. The question you're asking is really, for example, in this picture here, is for that blue chain, for example. Ask yourself, what's the right word to say? I mean, the challenge is this. You got this backbone, which is the blue chain. It will break if you reach 3 nanonewtons. On the other hand, this blue chain is wrapped around with the red chain, which is our junctions. If it takes much less force than 3 nanonewtons to pull out, then by definition, it will pull out instead of breaking. Yeah, that's obvious. That's completely trivial. Okay? Now, the rest is what I have not indicated in detail. That's this plot. We replotted the Winston's plot. We used our parameter of the area density. Well, of course, we don't know exactly how long is our area density. In other words, we know how to estimate from here to here. That's LC, as I indicated. So it come back to the plane 3 times. We know that. But just the fact you have 2 hairpins does not mean there will be a chain that's threading through. Right? Therefore, the only thing one can argue is that you will have a load-bearing strand that is structurally proportional to LC, but it could be 10 times larger than LC. Could be 5 times larger than LC. We don't have any result, theoretical result on that. That's the shameful thing, embarrassing thing I have to say. To figure out this, in theory, it should be doable. It's just you just have all the Gaussian chains inserted into each other. At least at some level, using some criteria, it should be possible to figure out what this is. And I have teased this with theoreticians in the world about it. Give me an estimate of this. What you need to recognize is to determine this, in principle, is a multi-chain problem. By definition, at least it is a double chain binary problem. And what I argued about LC, which is what Richard Wu argued about it, of course, is a single chain property. Okay? And the power of this that I bypassed is that I'm going to claim that the single chain characteristics is giving me enough insight from limit to claim that even when the multi-chain effect comes in, how many of such hairpins exist will be the key, right? In other words, if I need, let me use this representation. If I need to flip back this many times in order for another chain to find another pair, then this is my low bearing strength. See, right? And I don't know how many. I need to fall back forth before another chain get hold of it and form a junction with me. Okay? So in this plot, I just made some very arbitrary guess of what that length should be. And once you made that arbitrary guess, I find this slope is about 1/10 of the breaking force. And there are other arguments which is way beyond the scope of our lecture that can convince me that the breaking is not due to chancellation. Okay, so let me just close the argument, to the point of answering. You can read it. I have a book chapter where I argued in very detail why this breaking is not chancellation. However, this is not to be confused with the fact that chancellation could also occur. In other words, you can imagine, in fact, not other words, in fact, our more recent computer simulation will allow me to have the insight. I know that computer simulation is something actually I briefly mentioned. No, sorry, not in this class, previously. Computer simulation allows me to say that there are cases where the other chain really come here and form. I'm not going to do it properly, and form a knot. Well, you can understand it in the way of knots. Okay. In other words, not a simple, just uncrossable, but really wrapped up and can tighten, and that will prevent chain section, chain pull. Okay. In that case, if you have a couple of such cases where this thing is wrapped, then this chain breaking could occur. Okay, will occur. But these are statistically small events. They are not the dominant. They are not the cause. So with that, I'm closing my logic here. Okay, there could be a few, and computer simulation actually tells us why there could be a few, because there are a few that are wrapped with each other much more heavily than this simple, smooth hairpin kind of thing that can really slide on. There could be ones that, you know the whole thing. You know how you tie your shoes. I mean, there could be ones that are much tighter, that the chain has no escape until you build the force of 3 nanonewtons. By that time, of course, I may as well just give in, break up chain. Get it? Right? Right? So that's the point.
Okay. Thank you.
So so we touched a bunch of deep points. So that we're reaching a good point to summarize before I move on. So in any event, I will, in fact, skip a lot of the summary, perhaps just give you this one, so that you will see that this is something quite familiar. When I say that, I mean the following here. Remember the 5 factors I indicated for you before? 5 factors that can move the brittle-ductile transition point away and higher and lower in temperature. This is where this whole system, or this whole picture, has 2 sides. On one side, you have the driver. which is the backbone, which is the chain network, whose structure has already been analyzed. It's not entanglement structure, it's something new, per se. It's something, let's call it Richard Wood structure, in honor of him. That's the driver, right? That's where we ask about, hey, who is delivering the stress? Who is delivering the mobility in the name of Eyring? The other side is, how difficult is this job of delivering? In fact, that part is quite naively, you can just do it this way. Naively. It's not just so simple in that sense. Where do I have it? For just a second, where do I have it? Here. You can go back to this original story here. You can naively say exactly this. There are two sides. One is your success to deliver stress. That depends on the structure of your network. The other side is how sleepy your polymers are stuck being there. The barrier that you need to overcome. Right? Of course, the colder it is, the more closely packed they are, the more difficult to wake them up to give them mobility. So that's the two sides. The chain network and how dormant they are stuck in there. So given the fact there are two sides, it's easy to understand all these 5 features. Physical aging. Well, it gives you a bigger barrier. It's more difficult. Okay? So you need your network to be even more robust or denser. Then you can overcome. In other words, even upon aging, I will still stay ductile. By what? By, for example, melt stretching. In other words, if you have a ductile polycarbonate, you age it so that ductile polycarbonate becomes brittle. Well, the only way to overcome that is I take my polycarbonate, I first melt stretch it. Then even when you age your polycarbonate, it will still remain ductile. Because I have improved my network. So even though the soldiers are more dormant, you still will be able to wake them up. So this is quite obvious. So the physical aging, it just makes the samples more trapped. So I used the fact that a previously successful activation is no longer successful with aging. So we're representing this way. In other words, there's just not enough mobility created. And rejuvenation, remember you saw that magician's thing, that you pass through the 2-row mill, that styrene become ductile. Well, that actually rearranged all the monomers. In fact, all the monomers are almost half awake already. So it's very easy to wake them up. In other words, you have changed the energy barrier with the mechanical rejuvenation. So that interprets why this is happening. And what about pressurization? That's the 3 things that has nothing to do with chain network. The pressurization, a simple argument, is you smash it, now the sample in some sense is further densifies, right? But it's not a thermodynamic effect in the sense how sleepy the soldiers are, perhaps is less affected by pressure, is not sufficiently affected by pressure. But then there is the second part of the effect of pressure. It makes Chem pull-out harder to occur. So that I can improve that F pull-out force and therefore accomplish the job of activation before Chem pull-out takes place. So that's my interpretation. Very hand-waving, but totally satisfying to me without getting into any complications to appreciate what is the effect of pressurization, which makes polystyrene at room temperature ductile to hydrostatic pressurization. And the rest is also very straightforward. Melt stretching brings the network in the XY direction. You're drawing in the Z direction, much closer. Okay? By definition, because when you melt stretch, your cross-sectional area shrinks. So in the fine deformation limit, all the backbone collapses into a smaller cross-sectional area. And therefore, your job to activate becomes easier. And dilation has exactly the opposite effect. So that completes the whole discussion on the latest understanding at the Chen level that speaks about why polymer can yield and how a brittle-ductile transition arises. Questions? A very good point to pause. This is I recognize this is a lot in terms of concepts involved and results discussed. I have not seen anything better to replace this. And there's nothing prior to this that I know of that would allow you to rationalize the phenomenology, which is there is a brittle region and a ductile region. And all I want to say, perhaps at the end, is that you cannot design a theory that only explains why polymer can yield without confront the question of why when it stops yield, when it loses the ability to yield. So the very same theory has to explain both. You cannot have a theory like Eyring and just be content that I can explain why polymer can draw and yield.
Dr. Wang, I have a question.
Okay.
What do you mean by the chain network need to be robust? Does it mean that it need to suffer some stress before it activates its neighboring chains, right? It needs to be robust enough to suffering a certain stress before activating its.
That's right. Yes.
Yeah. Oh,
or rather, you basically as you draw, you will try to avoid your force building to the level of pull-up. That's another way of saying. And when you have a denser amount of chains, of course you achieve that before the tension building enough to have chain pull-up. So this is all logically totally consistent. In fact, one of the things that I'm proud of being able to explain, let's see if I have it here, may not. Yeah, it is here. So one of the things that I'm able to appreciate is this famous phenomenology, that polystyrene or PMMA, that's very brittle, okay? Very, very brittle. If you put it on compression, look at this movie shows. It's just, if I don't tell you it is anything, you may see that was honey or that was water. Okay? So, how people understood this? So you see, in compression, polystyrene is ductile. Well known. You may say, oh God, Eyring idea can explain this. Well, there are some papers that we wrote that you can take a closer look if you're interested, and to appreciate, indeed, compression is a very different animal than extension. Very, very different. I don't have time to go to the details of it. Very different. But the simple way people have explained this difference between extension and compression was that, through some big words, was that in extension there's something called dilational stress. In other words, when I extend, I always try to move things apart. When I compress, I don't move them apart. Okay? So, if you are not able to explain this feature, then you still don't have a good picture, or at least even just logically. To appreciate that, let me show you the other movie. So this is a polystyrene, a commercial polystyrene with a weight average molecular weight 300,000. If you reduce that to 50,000 and do the same compression, oops, it falls apart. So what does that teach you? What does that teach you? So it has to be long enough and reach out to each other and form a network. So it seems like the chain network is still important. Once you have a good chain network, like this one, like 300,000, we do have a good chain network, but it's brittle in extension. So why it refused to fall apart? Implying your network is not falling apart, right? By comparison, see the logic? I just showed you without network, you admitted without network it's not good. And therefore, this movie shows the network is still there by definition. And the question is why the network is still there? Aside from some dilational stress and pulling things apart versus, well, as you compress, if you like to think about your network has to expand this way, right? Radially, by definition. It also has to be displaced away from each other. Yeah, by definition. Okay? In other words, by definition, this network should, by definition, there is chain tension also to build up in the chain network. Okay? F will also arise as it fights. See, it's all shape changing, right? So you got a network. Now you're forcing it to change its shape. You want it to expand this way. Why that is happy? Why doesn't it build a force? Well, of course it builds force, but why it doesn't fall apart? So why it doesn't fall apart? Let me give you a clue. As you compress it, it builds so much pressure. The amount of pressure it builds is similar to the amount of pressure I use to pressurize my styrene from all directions to make it ductile. Remember, one of the factors of pressurization. So it seems the simplest idea is that in compression, I'm exerting pressure just like hydrostatic pressurization, which makes the chain pull out much harder. You have to reach much higher stress, much higher chain tension. So, I will continue to wave my hands because there's nothing, a first principle available, simply because this network is just so damn hard to treat analytically. But it seems quite satisfying to say that this is what happens with respect to the phenomenology. So it's my opinion that this sharp difference between styrene being brittle in extension and ductile in compression is, to me, by definition, not something you can explain satisfactorily without involving a chain-level account. You cannot treat this as a continuum and say, geez, it's just it's a different mode, and it looks, this different mode will just give me this result. I'm not happy with that. But that's what we had before. At least we have a language we can rationalize at this point, if you like. Let me just write it here. That basically the compression pressurizes and therefore raises the chain pull-out force level. So chain pull-out would only occur much later. By that time, you already activated. Remember, it's all about a competition between whether I have enough mobility so that they will just happily go along with the shape-changing rate. If it does, of course, there's nothing, let's go. So it's just a matter of how successful you can shape change, right? Yeah. Okay. So this really completes the discussion on only a tiny part, well, tiny, it's not tiny, of course. Only I'm trying to get to only the glassy part of it, right? So I'm trying to find my titles. Look like I'm losing it. But basically, we're in part 2. We went through several parts. Yeah, here it is. We went through several part 2, and in part 2, there's a part, and the A part is only on just glassy polymer. And there were several items of this A part. And so when we come back next class, we'll talk about the B part, which is semi-crystalline polymer. Again, something I can never speak about 2 years ago, because we didn't dive into the subject at that time. So we'll come back and talk about the B part, which is semi-crystalline polymer. And next week, we'll have a chance to talk about, in either case, a solid polymers undergoing fracture in presence of cracks. So that belongs to fracture mechanics. But before that, let me just bring you to speed on the topic we have touched today. So I'm going to go into some detail about it. So keep in mind that, let me just use this page to do it. Keep in mind that, remember that our several hundred billion pounds of polymers is we're using them all because they have adequate mechanical properties. We want to improve it so that we can use less, perhaps. But that's all, it's all about that. And because of that, I mentioned the word, we use it all because of its specific strength. well, which is just a word. I don't think I invented that word, but basically, it's basically you can indicate that as mechanical strength. I will define it. Divided by density. How about that? That would be my specific strength. And practically, you can think much more easily. You get the bar of certain size. You ask, what is the weight of this? For example, if I use the same bar, so this is plastic. I have the same bar, same size of steel. Of course, I have a rather different weight, right? By a factor of 8, the same bar, right? And of course, this for the performance you want, this may overperform. But if I don't care about the size, which overperform means for your steel, you can use a much smaller piece, right? But if I don't care about the size, then I would say, oh, I will use my plastic because it gives me enough mechanical properties. So in any case, I don't need to go into details other than to indicate to you mechanical strength, of course, is a top question. And you may even ask, gee, to answer that question, do you need fracture mechanics? So before we go too far, let's deal with what was available in the literature. So with that, I want to share with you this book. I know it's supposedly out of date because it was cannot remember, it's 6 or 7. It was more than 20 years old now. I don't think we made a lot more progress at the Chen level, apart from what I just described today. But let's go back to really, this is the beginning chapter statement. Let me bring a few things to your attention, because it sets the framework, sets the reference for you. Of course, this is a plot you're familiar with, but we'll see where we need it. So this is a beginning statement in the book. That really needs to be updated, of course. But let's go with it. So the first thing is what I already shared with you. The strength of a carbon-carbon bond is 3 nanonewton. Okay, that's known. Next, he's saying that let me consider a case where my chains could all pack. Well, a nice way the chain will all pack is when they undergo crystallization and form a lamella. I know you will learn about it in more details later. So if you like, oh, they are kind of connected here, connected here, connected here, here. Okay. He's saying the cross-section of the bonds coming out of by area has a density of this for polyethylene. Okay? How do you figure out, or how do we figure out in our language? Remember, looking at it, all the chains are like chopsticks sticking out to you. Okay? All the chains are sticking out to you like chopsticks. Therefore, the density is just what we went through, 1 over S. S is the little cross-section of the of your chain segment. You plug in your number. This is about 1.7 angstroms. You're plugging this as 1 nanometer is about right. Then what? This is exactly 0.17 nanometer square. He said it's 0.8, 0.18. I say 0.17. That's because I may have my cone length being 1.1. Well, basically, that's it. Right? So why he mentioned that? In other words, he mentioned about the cross-section area occupied by each chain. That's just this. Right? So I'm just patiently going through this for you. Okay. He says, read what's next. He says, oh, this implies the theoretical strength of a polyethylene crystal deformed in the direction parallel to the chain direction is on the order of 17 gigapascal. This statement has many problems, the least of which is how can you have access? Let me just be very accurate on this. How can you have access to such great strength of polyethylene crystal? Because our polyethylene is not a single crystal. Let alone, what does that mean? Your single crystal, each of the lamellar is a few nanometers. How does it go through centimeters? How do they connect? Well, it turns out it connects to amorphous region, blah, 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 blah. So that's why I use the word semi-crystalline polymer is like a composite with the crystal as fillers. So what's the big deal? The fillers have a lot of strength, but you cannot access them. Well, what really it means is something different. What it means is, give me a chain, let me arrange them as chopsticks. Which we tend to do when we spun fibers. This is the human innovation, magic innovation of polymer fibers. You can never appreciate that until this discussion, in some sense. In any event, he's saying where that 17 gigapascal comes from. No? That he's saying the strength of the polymer is 17 gigapascals. It is because it is just breaking force times pi. And if you compute it, it's exactly 17 gigapascal. Okay? That's the theoretical limit of your fibers, if you're able to arrange them in chopsticks and still somehow glue these chopsticks together. The only way to glue it is still not to lose not to lose chain uncrossability in some way. Then you achieve partially this result. And then he moves on and says, indeed, fibers could achieve 5. Close now, okay? Close. This is the magic. The fibers can indeed be as strong as your steel. Because you are in this condition, all the covalent bonds are fully utilized. No waste, because you don't have chance coming back and forth, wasting all your cross-sectional area without load bearing. So this is the inside of fiber. It's a tremendous innovation. Well, and they all did this. Well, you may say the spider did that too. Silkworm did that too. But they all did that before there's any really appreciation at this theoretical level. At least, yeah. Okay. So let's read patiently the rest of it. It says, in a glassy polymer, the packing of the chains will not be sufficient as crystals. Of course, in fact, not at all. It's a coil, right? So the orientation is random. Okay? Right? We, of course, acknowledge that. Yeah? Well, in English, what nevertheless means. However, it is clear that the measured strength of glassy polymers is on the order of 150. Isn't that what I mentioned when I reviewed for you the Winston data? Here it is, 150. Okay? This is what I went through with you. That the breaking must not have happened because it's 2 order magnitude, right? It's 2 order magnitude smaller. And it is right to say that the failure is because of failure of secondary bond, the covalent bond, the van der Waals bond. I think I'm going to leave you as homework meaning when we pick up tomorrow, as to what's the confusion in this statement. There is a horrendous amount of confusion in making this conclusion that when you compare 150 with 17, he concluded, oh, it means there's not much transition. That's wrong. Meaning that without, at least without, maybe the author knows, but without further deliberation, this is completely confusing. That he is comparing the observed strength of 150 with this limit. That is only true for fiber. In fact, I already gave you the clue what's wrong. So we'll pick up next time. Any questions? Let me just first turn off this so we can help it.